Welcome to class. Today, we're going to talk about existence and uniqueness of solutions to differential equations. So put your best thinking caps on. Let's not beat around the bush. Let's jump right in. The nth order linear initial value problem. If you remember, this is what an nth order linear equation looks like. Go back to take a look at that video if you need a quick refresher. It becomes an initial value problem as soon as I prescribe enough initial conditions. If I have nth order, I need n initial conditions. So notice I am telling you not just what the function at some point, I've called it x naught, is, right? I'm saying that the function or the solution y has to equal y naught at this initial point. But I'm also giving you information about its first derivative there, its second derivative there, its third derivative there, so on and so forth, up to the second to last order derivative, or the n-1th order derivative. If I start counting from 0, by the way, 0 to n-1, that's n of them. So the nth order linear initial value problem is an nth order linear differential equation with n initial conditions. And it turns out that these are guaranteed to have a unique solution on an interval containing your initial time or your initial input, x naught. Now, this probably doesn't sound very controversial to you because likely up until this point in your entire math career, your math teachers have just said, solve this equation, find this answer, do these steps. But it turns out in differential equations, the idea of finding a solution becomes a lot more challenging and maybe even a little ambiguous too. In fact, there are no guarantees that a given random differential equation even has a solution at all, let alone a unique one. And I'm going to show you an example of how just one tiny little change, a really subtle one, can totally throw this whole thing off. All right, so here it is. Now, the one obvious change that I made here is I'm only talking about a second order this time, but you noticed I've given it a different name. I'm calling this a boundary value problem, not an initial value problem. But it looks pretty similar. I'd encourage you to pause the video here and see if you can spot the difference between this and an initial value problem. Otherwise, I'll just jump into it. You'll notice I'm evaluating the function at different points here. I'm evaluating the function at two different points, not the same point. And by the way, the fact that I used y instead of y prime or here is just an arbitrary choice. Really, a boundary value problem just uses information from multiple points in the domain, and we would call these then boundary conditions instead of initial conditions. So okay, here's my second order linear boundary value problem. And I'll show you why this guy doesn't play as nicely as the initial value problem. Let's take a look. So here, I've got a second order linear differential equation. Omega is my dependent variable, and t is my independent variable. And it turns out this function has the general solution, c1 cosine 4t plus c2 sine of 4t. Now, just like in an initial value problem, I prescribe some condition at the point x naught, right? So let's suppose, or let's let omega of 0 be 0 for simplicity here. With that initial condition, I learn that, well, omega of 0, according to my model, sine of 0 is just 0, so that tells me that c1 times cosine of 0, which is 1, should equal 0. Okay, so from my initial condition, I've resolved one of my parameters in my family of solutions. And now I know that omega of t is equal to c2 sine of 4t. So far, I've applied one of my boundary conditions, that omega of 0 is equal to 0. And what I want to do is explore a couple of different options for other boundary conditions to see what happens. So let's take a look at a couple of different boundary conditions I could prescribe. I've already given one, so here's some more examples of other boundary conditions. Notice none of these are being evaluated at 0 also, so that's what makes them boundary conditions. So in this first case here, when I plug in pi over 8, I should get 0. Let's see what happens. I plug in pi over 8, and I get, well, sine of pi over 2, which is 1. I just get C2. That should be 0, and, well, duh, right? If I just have omega of t is 0, that's the trivial solution. That's not really interesting. So that one kind of counts as having a solution, but kind of not. Let's take a look at a different one then. Let's say I just evaluate it at let's say I give it a go at pi over 2. Well, I will get C2 times sine of 2 pi, which is 0, and 0 equals 1. Well, that never happens, right? It's not possible for 0 to equal 1. So here, I don't even have a trivial solution. I just have no solutions at all. One more go? Well, if I just change the output I'm supposed to get to 0 in this third case, well, then I get the statement that 0 equals 0. Wow, how cool. But what that means for the solution is that C2 didn't matter. Any value of C2 is a solution. So what we see here is that different boundary conditions give wildly different results. Here I had trivial only, or one solution. Here I got that there are no solutions, and here I actually got infinitely many solutions. So we don't always have the luxury of having a solution, let alone a unique one.